Welcome everybody. It's my great pleasure to host Çetin Meriçli, who is the CEO and co-founder of Locomotion AI, which is a leading developer of safe and reliable autonomous driving technology with a current focus of semi-trucks. So besides being a dear friend, he's an experienced entrepreneur and formerly a special faculty at the National Robotics Engineering Center of Carnegie Mellon's Robotics Institute. He has 2 decades of experience in leading teams on developing and deploying complex robotic systems for commercial, military, and scientific applications. And he has played key roles in over a dozen high-profile applied robotics projects. And he's a well-published expert in AI robotics and machine learning. Çetin, welcome, and we'd like to hear you.
Thank you so much, Hande. Thank you so much for very kindly inviting me and giving me the opportunity to present today. It's my absolute pleasure to be here, to be with this distinguished group. As Hande mentioned, I'm Çetin. I'm the co-founder and CEO at Locomotion, and Locomotion is an autonomous systems company with a near-term focus on automating the transportation, ground transportation, and an even more near-term focus on working on self-driving trucks, because supply chain is the most integral part of modern society, and we don't realize it on a day-to-day basis, but everything we do and everything we use relies significantly on an operational and efficient supply chain. And I'll talk a little bit more about what that means, why the problem we are going after is worth solving. But before going forward with that, I'd like to give a brief background on myself. I'm a computer scientist by training. I did all 3 of my degrees in computer science, and my master's and PhD focusing on AI and robotics. So I've been into AI and robotics all my professional life and a majority of my biologic life. I've been very, very fortunate to be part of super cool projects all over. I learned a lot. I got to work with always smarter people than I am, and that I'm super grateful for. In my grad school years, in my master's and PhD, I was focusing on robot learning, what it means to learn, what it means to know something, how do we explain a task to a robot, and how we get teams of robots to accomplish a common task, coordinating and communicating as a team. And one of the quintessential examples of that was being able to play soccer. I was a part of the Boğaziçi University's entrance to the largest robotics competition in the world, RoboCup, first with our 4-legged small robot dogs, and later on with mini humanoid robots. And then I came to Carnegie Mellon to pursue my postdoctoral research. And there I worked on service robots, again, coexisting around people, accomplishing tasks by interacting with people and learning from people. So there is a theme, if you start to sense that I was always interested in well-defined tasks, valuable tasks, and being around people and doing something on a robot to do something on its own to accomplish a task. Later on, I was super fortunate enough to be given the opportunity to join National Robotics Engineering Center, which really defined me as a roboticist for the years to come. And about 3.5 years ago, I left CMU along with a number of veterans of robotics there to start Locomotion to pursue this commercial opportunity. And when I was at NREC, I was, again, very fortunate to be part of extremely interesting projects. I was able to play different roles. I was able to lead many of the projects, and I was able to contribute as a researcher to many others. And most of these projects were along the ways of autonomous vehicles. So my interest started shifting from indoor applications of robots to outdoor applications of robots, and not just outdoor applications in very, very demanding, very, very challenging environments. Some military applications, some commercial applications in off-road environments, on-road environments, high speed, low speed, a different combination of everything. myself and my team, we learned a lot. We developed a significant amount of know-how, which we all agree how and why it's important. And more importantly, know how not to. We've tried a number of things and we've learned what doesn't work, even though sometimes it feels like a great idea at the beginning. So that enabled us to really train our taste buds on complex systems engineering and be able to make a couple of fundamental decisions using the first principles while taking the details, gory details of literal nuts and bolts of complex systems engineering. And we are heavily relying on those abilities now when we are making decisions at Locomation. I'm sure since it's a very a popular subject, especially in the last decade or so, I'm sure most of you have a great understanding of autonomous vehicles. But just as a primer, very quickly, without spending too much time on it, an autonomous vehicle effectively is a robot. And a robot effectively has three groups of functions that each mobile and intelligent robot this way or that way has. It all starts with making an understanding of the world surrounding the robot. So there is a sense component. A self-driving vehicle needs to detect the objects. In the self-driving vehicle case, it is other vehicles, pedestrians, traffic signs, other objects of interest around it. Detecting the drivable road surface, understanding where is the road and where is not the road. Lane markings in the road where you are supposed to drive in, what kind of a surface, what kind of a slope, what kind of a traction you have, whatever you can extract from the sensors of the vehicle. Once you have the static understanding of the world, the next important phase is intent prediction. Being not just understanding what are the objects in the world, but how the objects act in the axis of time temporally. What are they doing? What are they likely going to do in the next couple of seconds to a horizon? And lastly, depending on the particular application of the self-driving vehicle, self-localization. What kind of an environment, what kind of a world I'm living in, and where am I in that world? Sometimes it is important to know with global coordinates that I am on this part of the Earth right now, or whatever planet that you are operating on. Sometimes the application dictates that you can just get away with relative coordinates. With respect to a couple of objects of interest, my position is this. Once you have a good understanding of what is happening in the world, the robot needs to do a decision-making, go through a decision-making process and needs to come up with a plan, what needs to be done. And the plan has several resolutions, both against spatial and temporal axes. There is usually a mission planner, which you can think of it as, okay, so today I'm intending to do a drive. It's going to be a long drive. I'm going to do this over a day or so. Or it's going to be a short drive. I'm going to be mostly operating in the urban area. What are the high-level specifications of the mission that the robot has? One level below that is probably most analogous to Google Maps or Yandex or Apple Maps or whichever flavor of the maps you like to use. Once you know that what is the mission, that usually can be boiled down to what is your point A, where you are, and what is your point B, where you want to go, and what is the best path between these two, what using a road network, what is the best path that you should take. Once you know what path you want to take, the next level is a trajectory planning. So now I know that what path I should be following, what are the trajectories that I should be planning and I should be executing in order to follow that path as closely as possible. And once you plan a trajectory, you can then decompose it into vehicle control elements. What is your speed profile and what is your curvature profile? When you combine these two, that will result in the most high fidelity path planning capabilities. And of course, for each of these lateral, the curvature profile, and longitudinal, the speed profile, now you have to have individual controllers focusing on optimizing different error parameters. Once you know all of these, now it's time to actually start commanding the vehicle. You need to somehow figure out how to turn the steering wheel to achieve a particular curvature profile. You need to figure out how to decompose a speed profile into, do I have to accelerate, do I have to brake, or do I have to coast? Sometimes, depending on the application, you might want to have a control over the transmission. Most of us are now using automated transmissions, and it's not different for the autonomous vehicles. But even with that, depending on what kind of a road you are operating on, if it's a very hilly road, if you are going uphill, if you are going downhill, you might want to actually have an influence on the gear shifts of the vehicle. And beyond the basic controls of the vehicle, of course, you would like to be able to control the peripherals. You would like to be able to turn on and off the headlights. If there is rain, you would like to be able to turn on and off the windshield wipers, and so on and so forth. So you first understand what is going on in the world. You decide what is your reaction to that, what you want to do, and lastly, how are you going to do that? And depending on the application or depending on the design, this happens somewhere between 10 times to 100 times a second. So that is usually what goes on inside an autonomous vehicle, be it our vehicle or a Google vehicle or any other kind of self-driving vehicle. This is the main aspect of it. Let me talk about a little bit of the history of self-driving vehicles. The self-driving research has a very long history. It goes all the way back to 4 decades or so. At places like Carnegie Mellon, which is considered as the birthplace of self-driving cars, and other institutions like MIT or Stanford, there were research groups working on different flavors of self-driving vehicles. But what actually played a pivotal role was Darpa, when they decided to organize a series of challenges. The first 2 challenges were focusing on developing self-driving vehicles to just go from a point A to point B in a desert. And in the top right, you see a small clip from these challenges. Many teams attended. This is the Carnegie Mellon's entrance. Unfortunately, we didn't win this first challenge. Many teams have attended. Many teams have tried different architectural methods. Some of them succeeded to a moderate degree. Some of them completely failed. The first challenge, no one was able to finish. The second challenge, Stanford team was able to win that. And that actually kickstarted the era of an awareness towards self-driving vehicle by the general public. And Darpa then decided to repeat this challenge, this time focusing on urban driving. It was once we conquered that, we could build vehicles that could go in the desert where there are no obstacles, there are no dynamic obstacles, there are no other actors, there are no signage, there are no semantic rules that you have to worry about. They decided to see how far we can push the technology to actually come and maybe one day replace what we are doing as drivers of vehicles. So they organized what they call the Darpa Urban Challenge. That took place in a small mock-up of a city with roads, with intersections, with parking areas, side parked cars, other cars driven by experienced trained safety operators. And each team or each vehicle had to complete a series of missions, sometimes driving from one place to the other while obeying the traffic rules, sometimes just parking and leaving a parking lot. Carnegie Mellon's team won this challenge by a clear margin. And promptly after that, the Carnegie Mellon and Stanford teams, at least some people from there, joined Google to start the Google self-driving project, which eventually turned into Waymo, and which had a pretty profound impact on how most other companies later emerged in the scene approached the self-driving problem. So one thing the Darpa challenges did was to create public awareness towards self-driving, which eventually unlocked other things like funding. The other part was very important. It actually created the talent pool. It defined a standard project where a number of people, maybe 100 or 200 people starting with, spent a couple of years deeply thinking about and working on. And you can now see, almost without an exception, most of those people at several self-driving companies, either running the companies or started the companies or playing key roles at those companies. Okay, so that was over a decade ago. That was in 2007, almost 15 years ago. And Google car project started 13 years ago. For a while, for a long while, there was a quintessential hype cycle, because it almost felt like that with the Darpa Urban Challenge, we almost had the solution. There were multiple teams who were able to finish the challenge, and the challenge itself was, well, a challenge. It was not easy. So it almost felt like that if we could take this technology and just harden it a little bit more, we will just have self-driving cars, and not just have one or two of them, we would have millions of them. We would stop driving manually, because the cheap self-driving cars with great reliability would be here for us. And on the left side in the slide, you actually see, if you go a couple of years ago, like 6-7 years ago, everybody had extremely bullish, extremely excited, pumped, aggressive goals and expectations. And if you come to a couple of years after that, now we see the same people, the very same people, speaking very differently about self-driving cars. What once was just like 2 years away, or by the end of this year, or definitely within next 5 years, now 10 years later, it is maybe another 5 years, maybe smaller scale, maybe scope down problems. So, and sometimes some of the people basically just stop talking about the deadline at all. So they all say that, hey, like maybe one day, but we don't comment about that. So now we have to ask ourselves why, like what exactly happened here? Because this is a very curious case. Why autonomous driving is hard? Let's maybe start with that. Why do we think, why we have been going after this problem with billions of dollars in funding, the smartest people in the world spending their precious time on it? We are making progress, but we haven't cracked the problem. Why? So one of the things that, one of the fallacies here is that self-driving, especially with the level of technology we have today in a very democratized fashion, it is very easy to demonstrate, but it's very hard to turn into a robust product that can scale. And I'll tell you about why that is the case. One of the big things is that plays a role here is uncertainty. Uncertainty plays a very confusing role in the robots. Robots are not very good in handling uncertainty, especially induced by humans, because humans are also largely unpredictable. But then if you look at the video clip on the left, well, there are a bunch of people seemingly acting super erratically, but no one hits no one else. They somehow find their way. How do we do that? Maybe that's a byproduct of evolution. We as people, we are the prime generators of uncertainty, but since we co-evolved with each other, we also are inherently immune to the uncertainty, and we are extremely good at dealing with each other. We have very good ways of communicating, sometimes verbally, sometimes non-verbally. So you just look at something, you register something, and it tells you enough to stay safe and stay operational. In the meantime, we've been achieving great success with wide-scale robotics deployments in elsewhere, like such as warehouses, where you can actually control the uncertainty. And what now we know is that if we can control the uncertainty, the rest of the robotics is maybe not an easy problem, but it's a tractable problem. You can actually build robots that can last, that can work in a reliable fashion, and that can generate significant value. So one of the secrets then, it is my opinion and my company's view, is to scope the problem in such a way that we get to control the uncertainties, we get to work on the parts of the problem where we can at least have a bounded view of the uncertainty. We can operate in a closed world assumption, and we can just solve a problem for that scope down environment. If we can do that, maybe we'll have something that's actually operational, and we can use it as a foundation to then build more and more capable systems later on. So going forward, the self-driving problem, why there's uncertainty and why it's a tricky problem. It's more than just detecting the objects. I gave a deliberately reductive view of what a self-driving vehicle is. I said, hey, like, you need to understand what objects are there. Is there a pedestrian? Is there this? Is there that? Yeah, that's definitely true, but it's oftentimes is not enough. And as people, when we are driving, we register thousands of micro cues without even deliberately thinking about it, and we maybe make thousands of micro decisions. So there are semantic subtleties that we just know when we see them. So if you're on, suppose that you're on the road, you see a vehicle on the next lane, and you realize that there are dents on the side of the vehicle, or maybe the paint is chipped. Without even deliberately thinking about that, you realize that, yeah, that this vehicle has been through some challenges, and so maybe the person who's driving that vehicle is not a very good driver. So maybe you should stay away from that vehicle. And as a result, without again realizing, maybe you slow down, maybe you speed up, maybe you change lanes, and maybe you stay alive just because of that. In another example, you look at your rear view mirror, and then you see the driver behind you, and immediately you realize that, well, the driver is not paying attention to the road because the driver's eyes are not on the road and probably looking at a phone. So as a result, this is probably a distracted driver, and it poses an increased amount of risk. And the reason why we can understand this super easily is that in an evolutionary way, all creatures are wired to detect gaze extremely well, because in the wild nature, if something is looking at you, most likely that thing has a plan to eat you. So it's very important for your survival to detect gaze in a very capable fashion. So you detect this and you react to this without even realizing it, because that's like hundreds of these happen on every second. The other area that's very tricky, very easy for humans, but very tricky for machines, is the whole context and common sense. So if you look at this top right picture, there's a guy protesting something. There's a traffic cone on the head, and there's a stop sign at hand. So this is a perfectly legitimate stop sign, and that's a perfectly legitimate cone. But if you detect them as cones and stop signs, you are not supposed to stop here, or you are not supposed to take that cone seriously, because clearly there's something else going on here. And that is so simple and so understandable for people. It is so incredibly difficult to explain it to machines who know nothing but just number crunching. How do we even define context? So this is one of the big problems, or big challenges rather. And then the world is so rich, so colorful, and so full of great variety of edge cases. And edge case is becoming a misnomer. I will say something about it in a later slide. But when you are preparing your system, there are things that you can't even imagine. For instance, most likely if you are training your system, if you are using machine learning for your system, you probably don't have a person in a chicken suit in your training data. You probably don't have a fighter jet going in the middle of the road in your training data. If you have a number of pickup trucks in your training data, probably none of them have a half pickup truck that actually like halfway into a very large pothole. So these things, and maybe a billion, maybe a trillion different things like that, are out there lurking in the real world, and we don't even know what they are. That's why they are edge cases. So these are some of the elements that are perception challenges maybe, but they are not just about detecting objects. They are not just about pixel by pixel classification or just number crunching. There's something else here that we don't quite have a good grasp on yet. Another great example, one of my favorites. So again, at the beginning, I mentioned that, well, you have to detect the objects and you have to detect whether there's a pedestrian or not. Sure. we can detect whether there is a human on the side of the road or so. But look at these two pictures. And I also mentioned intent prediction. So ideally, we would like to understand if there's a pedestrian, what that pedestrian is likely going to do in the next couple of seconds, because that will impact what motion you will be planning for your next couple of seconds. Because nothing is instantaneous in the real world. You have to be prepared to accelerate, to decelerate, maybe to come to a harsh stop if something funky is likely to happen. So let's say we are trying to estimate the probability of jaywalking here. And it's very easy for a human to look at the left picture and say, oh, like, well, I mean, there seems to be like a little kid and what seems like his mom. And they probably won't just jump into the road. Like that's probably something that they won't like to do. But when you look on the right, there are a bunch of teenagers with skateboards and they are on the side of the road. Well, the jaywalking probability in the right case is a little bit higher than the left case. And this is, again, something we don't have to number crunch, we just know. Because we have enough background information on that and we have enough reasoning capabilities. This is incredibly difficult to, again, reliably explain to a machine today. So one of the, this is a little bit of a crowded slide. When I have time, I'm planning to decompose this slide into a couple of slides, maybe. When we are developing a system, one of our hypotheses is that we will develop the system, we will do a period of field testing, and if we can test it enough, we will see everything that we need to see to generalize the system for its later on deployment. In other words, we actually anticipate that we are operating in a world mostly governed by something like a Poisson distribution with random independent arrival rates. So the distribution here is, it starts, you cover, and over time, at some point you reach to a point where the area under the curve is finite. You've seen whatever you need to see, and you basically understand that universe. What we hypothesize, not just me, but like several experts in the safety field, hypothesize that the real world is most likely more closer to a Pareto distribution with a heavy tail. So sure, you can actually cover a great deal in the initial testing period, but there are always enough edge cases and they will keep coming, and there is no way of capturing all the edge cases just by brute force way continuing to test. So you need to think in different terms. You need to think in less brute force terms and more in maybe ontologic and more generalizable terms. Like how can you govern certain principles where you actually develop a capability, test it for the requirements and specifications of that capability, and once you do that, you make sure that you are covering a large portion of the universe without necessarily seeing every single instance of what otherwise would constitute an edge case for that. That again is easy to say, difficult to achieve, and it requires a different thinking about the problem and how you approach it. I've been in machine learning this way or that way for about 20 years. And when I was a very young grad student, when I was starting, the first wave of neural networks were gone. It was the age of the fuzzy logic. And fuzzy logic was in also slowly phasing out. Support vector machines were just coming out. For a little while, everybody was crazy about support vector machines, and SVMs were the cure to everything. Before that, fuzzy logic was cure to everything, and before that, neural networks were the cure to everything. And none of them were, of course, cure to everything. They were cures to maybe a lot of things, but not a universal thing. And then around mid-2010s, deep learning made a comeback. It's basically neural networks in disguise and maybe beefed up neural networks. And since then, everybody has been thinking that, well, we've actually cracked AI. All we need is a little bit more data and a little bit more compute, and this fabulous architectures will figure it out for us. There are a couple of problems with that. And now, again, we are starting to see more and more voices being raised around potential limitations of today's deep learning-based systems. This is not a categorical criticism of deep learning. It's an extremely powerful paradigm for certain tasks. But today's architectures are really brittle against adversarial inputs, natural or artificial adversarial inputs. It's really easy to sprinkle something on an input and really throw the output of a neural network significantly. And that's a very active, brilliant research area that a lot of smart people are working on that. But today, this is still the case. They also are known for very poor generalization for out of distribution inputs. So as long as your training data, test data, they all come from a relatively same distribution, we have good ways of covering that. We have satisfactory results. But for real out of distribution inputs and Q edge cases there, because edge cases are out of distribution inputs because we haven't seen them before. Deep learning methods are still a little bit iffy. Another big issue, especially when it comes to safety critical system development, is that you first need to be able to understand every single thing about your system so that you can basically write specs around it, develop the system around it, white box test it, and make sure that you covered basically everything. There is nothing that you don't know about that system. And that's not necessarily the case with deep learning, because these are gigantic structures with hundreds, sometimes billions of, maybe tens of billions of parameters, depending on what domain you are working on. And there is a tendency to make the models bigger and bigger and bigger, or there was at least. Now people are starting to realize that it takes millions of dollars to train one model. So now the reverse trend is starting. How can we get away with a smaller model? But nonetheless, the reason why we call deep learning a deep learning is that there are so many layers. And as you go down in the layers, it's really dark there. We have no introspection abilities in really truly understanding a couple of things. What it actually learned once you train a model, what it actually learned, how it actually learned it. Of course, we understand how we are training it, how we are propagating error, how we are doing regularization, etc. But why it learned it this way and not the other way, how the learning actually took place. So these are still super simple but valid questions. And if you cannot answer these super simple questions about a very important component of your system, you will be very challenged to put that system into any critical decision-making path. So that is another open problem. The last thing is a little bit maybe more on the nerdy side, but I find it very, very fascinating. Deep learning or not, any machine learning system, or beyond that, any statistical inference system under the hood assumes the data that you are using to run this inference process to be identically and independently distributed. And in real world, for a robot, that is not the case, because you perceive, you get a set of data from your sensors, let's say. You use that data to go through the sense, plan, act paradigm that I mentioned at the beginning. You make a decision and you act on the decision. And as the result of that action, you get another set of inputs in your next decision-making cycle. So what that does is the next set of data points that you will get are actually dependent on the previous data sets, because that previous set of data impacted how your robot will act, which in turn indirectly impacted what next set of data you will get. So we are actually fundamentally breaking the IID assumption. So what is the extent of that? Is it actually important or not? There are, again, some academic people are looking into that. I'm a former academic. I no longer am allowed to do any of these things, unfortunately, but I'm allowed to chime in every now and then in venues like this. So this is a very important problem, and very few people have actually been aware about that. And I think that's also something that we need to understand properly before we put a giant blob of a black box into the life and death decision making of driving a vehicle. So all of this, I'm now walking you through my argument construction, why autonomous driving is hard, what are the open problems. The real world is very rich with a lot of edge cases, and our current methods don't seem to be faring well with this out of distribution, like unknown unknowns, if you will. So to repeat that, an edge case is by definition something that we can't even talk about here. Because if we can imagine it, we can then design a system about it, we can then test a system about it. It's just a scenario, it's not an edge case, it's just a case. Everybody normally, when talking about safety, focuses on, well, what happens if something breaks? Great, you definitely have to do that. Functional safety is extremely important in safety critical systems. But what is also very important is your system safe enough when there is nothing broken? In other words, what is the safety of the intended functionality? Is your intended functionality, when everything is going well, is it safe enough? How are you going to prove that? Proving a safety case, proving your safety of intended functionality against edge cases is a very non-trivial process. Of course, when you look at the autonomous driving landscape, a lot of people, including us, heavily use simulation, different forms of simulation, and track testing, closed course, so that you can actually control the environment, you can run controlled experiments, etc. This can help, and these are integral parts of the development process. But that's not just it. What we also need is a very safe and very large scale way of exposing the autonomy to the real world as much as possible, so that we learn as many of these edge cases or interesting situations in the world as possible. Because simulation is fundamentally interpolation. You cannot simulate something that you cannot imagine. And edge cases are out of distribution. Again, we just established that there are things that we know, and there are things that we don't even know that we don't know. We have to cover as much of that possible. And this is an uphill battle. We also know that we won't be able to have 100% coverage. But what is that good enough? What is that safe enough coverage of it? That goes through significant real world exposure in a safe way. And why it needs to be profitable is that because you need vast scale. And if you don't have an economic reason, commercial reason to do so, it's going to be very difficult to build and sustain a test fleet of that large size. Lastly, now I'm bringing you to why Locomation is operating in the field that we are operating, why we are focusing on self-driving trucks. When we looked at the overall transportation industry, freight transportation immediately caught our attention as a very large opportunity. And we also were hypothesizing that over time, people will commute less around. And if people are not going to things will have to come to people. So freight transportation is already very large, very important, and it's only going to get more important. Of course, when we were hypothesizing about that, we were not thinking about a pandemic coming in and making all of us just like locked down in our homes, not being able to go anywhere. So everything really has to come to us in this case for safety reasons. But nonetheless, we are now here. That trend was already happening, but pandemic probably accelerated it by at least 5 years, maybe a little bit more. The problem here is that there are three big pillars that supply chain is now looking at, and that's why we have some issues. There is an accelerating demand. Everybody wants to ship more things around, wants more visibility and predictability around those shipments, and wants to pay less for it. The supply chain has historically been inefficient and has been struggling to meet the capacity demands. But lately, the biggest driving factor there is a growing shortage of skilled truck drivers. Truck driving is a long-haul truck driving, especially, is a very demanding job. It doesn't pay all that well for all these demands that come with the job. And as a result, very few younger people are coming into the industry or choosing to stay in the industry. So the result of that is an aging and shrinking population of truck drivers, which basically further limits the supply. So it's a scissor effect. The demand is growing, but the supply is going down, and the tension between the two creates most of the problems that we have today, including the New Year and Christmas presents to be delayed, and all kind of back-ordered items that I'm sure most of you are suffering from. So this is the practical parts of the supply chain. And then there's the whole carbon emissions crisis. So now, again, we are realizing day by day is that we really do have a carbon emissions problem, and we need to be super mindful about it, and we need to do something about it now. We cannot wait for another couple of decades and keep burning fuel and just go as we've been going for the past couple of 100 years since the Industrial Revolution. That's not sustainable. And road transport actually, and long-haul trucking accounts to a significant portion of the carbon emissions. And you need to have a way of doing whatever you can do to reduce those carbon emissions today. And what we are doing, which is now coming finally, addresses all these three pillars. What we say is that the fastest way to start deploying autonomous vehicles, autonomous trucks, and be able to deploy them at scale goes through a concept we termed human-guided convoying. It is a convoy of 2 trucks, and initially there will be a driver in both trucks, but when the convoy is operating, only the driver in the lead truck will actually be driving. The driver in the follower truck will be sleeping in the back part of the truck, and the second truck will drive itself. It's a self-driving truck, but it's only self-driving as long as it stays behind the leader and it follows the footsteps of the leader wherever the leader goes. What that does is we don't have to deal with out of distribution edge cases because we still have a human in the lead who will be able to make those high-level judgments and high-level decision makings, while we are still tapping into the benefits of self-driving in the follower vehicle, because one driver gets to effectively make 2 trucks move at a time. And every now and then, the 2 trucks can swap places, so the 2 drivers can make sure that they spend enough time behind the steering wheel and enough time resting. You can practically get a convoy operational 20+ hours a day, every day with this system, which is a tremendous value add. The way it works, or it will work in the commercial setup, is that the beauty of it is, since we will have 2 drivers and 2 trucks, you don't have to worry about driving a semi-truck in complicated urban areas. You can let the humans drive it, and you can focus on automating the middle mile that happens on an interstate or a highway, and that constitutes over 90% of the long-haul routes anyway. So the majority of the action is already happening on the highways. And if we can automate the highways, that's a great way to start. We don't need to solve all the complexities of the urban driving at the beginning and at the end. That is also this 2 truck, 2 driver convoy system enables us to deploy faster. And here's a video from a real world pilot that we've done with our first customer. So here you see 2 of our trucks pulling 2 of their customer loads. And we are taking a look at from the follower vehicle. So it drives itself and it just follows the lead truck wherever the lead truck goes. So today we are still in the development and validation phase of the technology. That's why there's a specifically trained safety driver ready to take over behind the steering wheel, but the driver is not actually doing the driving. The truck drives itself. If you look at the what's happening under the hood, what it means, like how the system is working, I'll show the hardware design of it, but we have a multitude of sensors, including cameras, lidars, and radars. And what we are doing is the top object that we care about in the world is our lead truck. We always know where we are with respect to our lead truck, and we religiously track the lead truck and follow it. What we compute is the breadcrumbs or the footsteps or the wheel steps, in this case, I guess, of the lead truck. And if we can count those breadcrumbs, those actually give us a reference trajectory. So if we recall my super reductive overview of the self-driving vehicles, I mentioned about mission planners, path planners, trajectory planners, and then controls. We actually don't have to worry about mission planner, path planner, and to some extent trajectory planner, because our leader is giving us a trajectory that we just need to follow. The advantage of that is it is extremely easy, incomparably easier to validate. It confines the autonomy to a limited universe. By just following the lead driver, we can actually navigate through interesting real-world scenarios like work zones, construction zones. We can speed up, we can slow down. We don't have to make any of these decisions initially by the self-driving vehicle. It just can be done by the lead driver, and the follower just follows it. So this is how the system perceives the world and how it operates in a nutshell. And when we look at what's quite literally under the hood, what's going on here, we are working with the global leaders of automotive parts and trucks. We have partnerships with the largest engine manufacturer in the world, Cummins, for deep integration into their powertrain, including their engine and their transmission. We have a partnership with ZF, again, another global leader, for joint development of redundant steering. And redundant steering is very important. Redundancy here means there are two sets of electromechanical contraptions controlling the steering. They are always in sync. This way, if one set fails for whatever reason, you have a backup. And combined, these two actually help us reach the reliability levels that are required for safe operation of these vehicles on the streets. Similarly, we are working with Bendix, another leading brake provider in the world, for redundant brake systems. We have a partnership with NVIDIA on all this number crunching that we need to do from all the data from the sensors and all of our autonomy algorithms. We have our patent pending approach to sensor placement. We consolidate all of the sensors into side mirrors. This way, it is easier to manufacture and assemble a side mirror with all the sensors. It is easier to field replace. If something happens, you just need to replace the mirror. You don't need to worry about the individual sensors. It provides the best coverage, both sides of the truck, near over 300 degrees coverage around the truck. And since they are about 3 meters separated from each other, if the rest of the system is properly designed, that also provides a redundancy. If you for some reason lose one of the mirrors, you can at least limp along until you reach a safe stop. So this is also very, very important. And going back to the value proposition of that, why we even care about it, this concept enables us to deliver twice as much cargo to twice as far and twice as fast, while reducing the per mile operating costs by around 30% and reducing the greenhouse gas emissions by about 22%, which is a significant number, because this way or that way, whether we like it or not, for the long haul trekking, we are kind of stuck with the fossil fuels for some time to come. The ideas of electric and hydrogen are great, but electric trucks are not suitable from their range point of view for long haul operations, which are typically 500 miles, give or take at least. And hydrogen is there and viable, but not commercially attractive. It's still about 3 times more expensive than diesel. We are starting with this Convoy system, but are we going to stop there? No, we are not a Convoy company. We intend to solve autonomous driving at the end of the day. The nice thing about our approach is that it has a very progressive expansion path to one day driving without a lead driver in front of the trucks, and one day driving not just in the highways, not just on the interstates, but also in the urban areas. We are starting with the 2-truck, 2-driver Convoy system, which basically looks at a 30% cost reduction. And then we will be increasing the capabilities and increasing the value proposition all the way up to 45% when we one day get a truck to drive itself with no human involvement on the highways and the urban areas combined. Again, the beauty of this is our initial starting point, which is substantially simpler than the end goal, captures about 2/3 of the overall value possible by autonomy. So that's a great start. And of course, on top of that, whatever we can do to advance, we will. But this is by itself a very compelling case study. So as we are getting to the end of that, in general, if we wrap up, autonomous driving has a very long tail for testing and validation because the real world is very real and very colorful, and there are all kinds of interesting things happening there. Heavily deep learning based approaches today, and that can change tomorrow. That's why we have scientists, have several shortcomings. They are very brittle. They are not explainable. That makes it inherently difficult for safety critical systems and dealing with the continuous non-IID aspect of the real world data. If you want to solve this problem, we somehow need to understand the problem better. And the only way to do that is to find a clever way of exposing the technology to the real world in a safe and profitable way at scale. And we believe human-guided convoying ticks multiple boxes. It basically offers a compelling value proposition that starts addressing the chronic pain points in the supply chain, including the capacity crunch, including the driver shortage, including the greenhouse gas emissions. And it also gives us a platform where we can actually tap into it and start getting relevant real world data at a vast scale. And the shameless plug bit of it at the very end is that Locomotion intends to be the first company to launch an autonomous tracking solution at scale. And we are still on track to be the first commercially relevant operation in the world. With that, thank you so much for listening. To repeat, our goal is to launch early and scale faster. And this way, we believe we will be able to make even more scientific and engineering progress, not just the commercial value. And this is our team as of last July, which we grew another 50% since.
Well, thank you very much. It was very eye-opening for me. Well, there are a bunch of questions already in the chat, and I also would like to get questions from the audience. So Mustafa Yaman asks, in the mission planning, do you need or use available maps or elevation data, etc.?
Yes and no. That depends on the mission, I guess. Of course, a prior map of what you want to do, what kind of environment you are expected to operate in is going to be helpful. The actual granularity and the content of that map is depending on the application. We actually don't think HD maps, high definition maps are absolutely necessary. There are different ways of doing that.
No. But currently you don't need them, right?
Currently we don't need them.
No. There is another question. Can you explain more about power law variable rate 80-20 rules? Yeah,
that's the part where we will leave it to the readers. Again, the keywords there are to go and compare the Poisson distribution and a Pareto distribution. If you look at these two, a Pareto distribution is a heavy tail distribution, and a Poisson distribution is just your typical exponential distribution.
And is there an alternative models, or are you working on alternative models of your IID systems?
Yeah, what we are doing is here super bypassing. We don't use machine learning at all right now. That's the beauty of our system. It's completely introspectable, and it is developed with traditional computer vision and geometric perception algorithms.
Ah, okay. So all explainable, and you know what
it's all explainable, and it is tractable to develop a system that will do basic things like object or positive obstacle detection, road detection, leader detection. You can do most of these things with great reliability without actually going into data-driven approaches. But of course, in the future, once you have this basic foundation in place and validated for safety, it will be easier to build semantic layers on top of it using some data-driven approaches. And then we will have to work on all of the issues that I actually listed as challenges and how to be, I mean, you can still use machine learning as long as you are using it in such a way that there are guardrails around it that will guarantee some performance boundaries and some safety boundaries, and the guardrails themselves are explainable. So there are some architectural ways around that.
Okay. Well, there's a question about the laws on driverless driving in US. What is the situation? What happens when a damage occurs to someone by a crash?
Yeah, let me first talk about the regulations. In the United States, the regulatory landscape is growingly supportive of this. So there are already more than half of the states have supporting legislation for this application. And from a federal government standpoint, our human in the loop model is actually compliant with the federal laws. The completely driver out, solo driverless models are not compliant with the federal laws because there's no way for the law enforcement, like the highway patrols, to interact with completely driverless vehicles. There's no agreed upon standard, there's no training, there's no protocol around it. And in our case, you don't have to interact with the machine. You can just go and talk to the driver in the lead track. And the second one, it's not an edge case because we are talking about it. And this is one of the most common situations. So what I like to call these are off nominal cases. So there's your nominal operation. There are a slew of off nominal cases that you actually know they are going to happen. And a vehicle cutting in between the two is one of those. So what we are doing to prevent or reduce that is, first of all, these guys are operating at 65 miles an hour, which is like over 100 kilometers per hour. And they will be about like 12 meters apart. So two giant things going that fast and with a narrow opening between them, you can still fit some vehicles, but you have to be a trained stunt driver effectively, or you have to be really, really persistent. In real work, most of these cut-ins happen if someone tries to take an exit on the right or merging in the highway and trying to go to the left lane. So they are very transient events. As long as it's transient, we don't have to do anything. We are fine with that. If someone comes in and insists in staying there, the convoy will immediately realize that, alert the lead driver, and if the intruder does not leave, the convoy will start slowing down to encourage the intruder to leave.
Yeah. Well, you call them intruders.
There are other things that we can call them, but let's stick with intruders for now.
Well, Turkish drivers, maybe.
Turkish drivers, okay.
Okay, so that answers that question. Yeah, actually, I had the same question. What is the worst case scenario for the follower truck in the sense, plan, act process? And I would like to ask in a different format. What is the worst case that you have seen? What is your worst edge case? What was it?
I mean, some form of fault or failure. And depending on the fault or failure, again, what we are spending most of our time is enumerating what can go wrong in the system and designing a system in such a way that is no longer your worst case. That is something that and ideally there are types of faults and failures where you can detect them. And once you detect them, you just recognize them to be taken care of later on, but you can keep your operations. Sometimes some faults and failures will dictate that you have to degrade, gracefully degrade, but you can still get to keep operating for a while, not in the same capability, but until you come to a safer stop. There are certain faults and failures where you actually need to look to execute a minimum risk condition maneuver. In other words, like a pullover and stop in the safest way possible as quickly as possible, because it's you are degraded severely. So the sooner you can stop, the better. If you cannot do any of that, and we intend to make it a very, very small fraction, a negligible fraction of the time, you can always try to stop in lane. But contrary to maybe the intuition, stopping in lane is not a safe operation. It's actually a horrible idea. So, and should be spared for absolute dire situations. Mm-hmm. And of course, you can imagine that if we do our jobs right, we can't even calculate how low that probability will be. But you can have a completely unexpected thing that will render all of your systems inoperable at the same time, at the blink of an eye, and you have no recourse. If something like that happens, yeah, you have an accident at hand. But again, all the safety engineering that's going into the system is to prevent that. And there are a slew of techniques that we are using there. The details are too detailed to cover here, but you try to understand faults, you try to decompose the system in such a way that there is no way that one fault can render the entire system inoperable.
Okay, we have more questions. Mehmet Akif Akkuş raised the hand. You're muted.
All right. Thank you for your presentation, Çetin.
Sure.
Actually, there's also some projects which is really similar to what we were doing. Scania, for example, has IQ-matic software, and they are also developing autonomous transportation systems. So, what is the difference? What's the different parts in your projects?
Yeah. So one of the things I think we are doing differently than most other autonomous companies and some other maybe platooning efforts that some truck makers are going after is our overall approach to autonomy and the way we decompose the system and the way we sequence the development. So it actually follows what I try to walk you through. The world is a gigantic semantic construct. There are things that are happening at a very abstract level. There's an obstacle, there is an object, there's a moving object, etc., all the way down to very detailed semantic understanding. Well, there is a purple car with dent on the side. There is this on the left, and there is this mother and a kid, and there is this teenagers with skateboards. So the level of understanding, the level of semantic understanding can go in very, very detail. What we believe is that one has to have an autonomy approach that actually encompasses all of these abstraction levels and not just operating in the bottommost semantic part. In other words, what we are doing is not just collect data, label it to be one of the, 100 objects that you know, and try to see if you can classify everything into one of these 100 objects. The real world has more colors around it, and that has implications in the rest of the autonomy stack as well. We have our own proprietary ways of doing motion planning, and motion planning actually requires intimate understanding of what your platform is capable of doing. If you can understand what the platform is capable of doing, you can then use those capabilities to plan a plan where your platform can actually execute it very accurately. So just to give some names, if you remember the little videos that I showed from the truck with the breadcrumbs, the leader following, we are able, so that is in that video, the trucks are operating at 65 miles an hour. And see, at 65 miles an hour, our follower truck is able to follow the leader truck with, on average, 2.5 centimeter accuracy. To get to that, and these are 40-ton trucks. If you look at the scale of the vehicles, the speed in which they are operating in, and the accuracy of what we are able to do, again, it requires an intimate understanding of the capabilities of the system. And we do have that intimate understanding because mostly of our past work, especially in the military domain. Military applications really require that understanding. They want to understand the physical limitations of the vehicles so that you can push the vehicles to the edge of their safe operating zone, but not an inch further. So these are some of the things that we are doing differently than some of our peers. To the best of our knowledge, of course, we are not living inside their brains or inside their labs, so they might be doing things similar to us or completely different than us. What I'm saying is just based on what's publicly available about them.
Thank you for that. I have also another question.
Sure.
Actually, while you're doing autonomy in your project, it is so much possible to have unexpected things to happen. For example, your system should be reactive to the unexpected behaviors, such as the fuel tank, for example, get damaged and you put all your fuel and then actually you need to stop, right? Yeah. But you can realize that unexpected behavior and you can change your plan to go to the nearest gas station, for example, or nearest mechanic part, mechanic to maintain the problem. So what is your algorithm to change the plan reactively? I mean, while you're driving, you need to change the plan. So what is the criteria?
Yeah, it's exactly as I mentioned. So you have layers of operating characteristics. By default, you are in your nominal operating mode. But it all starts with the fundamental requirement of being able to detect faults and failures. So you need to architect your system in such a way that when something like that happens, you will know, like the system will know that happened.
So my question is actually, what is the techniques? What is the algorithm? What do you use? It is like finite state machine or something?
It is, at the simplest explanation, it is a lookup table. Am I operating with full capability now? Yes or no? If not, how degraded am I? And if you lose a fuel tank, that's one form of degradation. If you lose sensors, that's another form of degradation. If you lose all of your sensors, so there's like a degree of what capabilities you retain, what capabilities you lost. And based on that actually limits or constrains your action space. There are things that you can safely continue to do, and there are things that it's no longer safe to continue to do. And depending on those, as I said, you will have a spectrum of responses from just like continue as is, but just remember to, I don't know, change the oil, or remember to do something about it when you get to the other end, all the way down to stop everything you are doing and just like stop in lane, and a variety of responses in between. So it's not just like I'm going to plan it once and hey, I'm going to just like do it no matter what. It's not like that. It cannot be.
Actually, Scania in their projects, they are using behavior trees to reactively plan the what will be the action when the unexpected things happen. I mean, actually, I mailed you 1 year ago, but we were trying to create a meeting, but actually we didn't succeed. Doing my PhD research, actually, I had a look at behavior trees. Yeah. That's why I'm asking.
I like behavior trees. In another project, not at Locomotion, but in a different project, we are actually using behavior trees. Again, that's a nice implementation choice. Fundamentally, it's not a theoretical difference, but I would prefer behavior trees over finite state machines, because actual implementation of finite state machines is a pain. But other than that, like that's an implementation detail. We are agnostic of what actually will be implemented. The architectural decisions are more abstract than that.
Okay, thank you for your answering.
Of course.
Okay, I think we are out of time.
I talked a bunch.
No, no, I really wouldn't want to take too much of your time. Well, thank you for your presentation. Let me stop this recording.